Hey everyone. In this presentation, I'll go through some notes from Chapter 1 of book Designing Data Intensive Applications. The Chapter 1 is called Reliable, Scalable, and Maintainable Applications. So this is the image associated with Chapter 1 of Designing Data Intensive Applications book. As you can see, it has three kind of scrolls. One is reliability, second is scalability, and third is maintainability. And we'll go through the notes in each of these categories. So reliability. Everybody has an intuitive idea of what it means for something to be reliable or unreliable. For software, typical expectations include the applications performs the function that the user expected. It can tolerate the user making mistakes or using the software in unexpected ways. Its performance is good enough for the required use case under the expected load and data volume. The system prevents any unauthorized access and abuse. Now let's look at the hardware faults. When we think of causes of system failure, hardware faults quickly come to mind. Hard disk crash, RAM becomes faulty, the power grid has blackout, someone unplugs the wrong network cable. Anyone who has worked with large data centers can tell you that these things happen all the time when you have a lot of machines. Hard disks are reported as having a mean time to failure of about 10 to 50 years. Thus, on a storage cluster with 10,000 disks, we should expect on an average 1 disk to die per day. First response is usually to add redundancy to the individual hardware components in order to reduce the failure rate of the system. Disk may be set up in a RAID configurations, servers may have dual power supplies or hot swappable CPUs, data centers may have batteries and diesel generators for backup. When one component dies, the redundant component takes its place while the broken component is replaced. This approach cannot completely prevent hardware problems from causing failures, but it is well understood and can often keep a machine running uninterrupted for years. Now, let's look at another class of reliability, which is software errors. A software bug that causes every instance of an application server to crash when given a particular bad input. For example, consider the leap second on June 30th, 2012 that caused many applications to hang simultaneously due to a bug in the Linux kernel. A runaway process that uses up some shared resource like CPU time, memory, disk, or network bandwidth. A service that system depends on that slows down, becomes unresponsive, or starts returning corrupted responses. Cascading failures, where a small fault in one component triggers a fault in another component, which in turn triggers further faults. There's no quick solution to the problem of systematic faults in software. Lots of small things can help, carefully thinking about assumptions and interactions in the system, thorough testing, process isolation, allowing processes to crash and restart, measuring, monitoring, and analyzing system behavior in production. If a system is expected to provide some guarantee, for example in a message queue that the number of incoming messages should be equal to the number of outgoing messages, it can constantly check itself whether it is running and raise an alert if a discrepancy is found. Now let's look at human errors in the context of reliability. Humans design and build software systems, and the operators who keep the system running are also human. Even when they have best intentions, humans are known to be unreliable. For example, one study of large internet services found that configuration errors by operators were the leading cause of outages, whereas hardware faults, servers, or network played a role in only 10 to 25% of outages. So here are some best practices. We should design a system in a way that minimizes opportunities for error. For example, well-designed abstractions, APIs, and admin interfaces, making it easy to do the right thing and discourage the wrong thing. However, if the interfaces are too restrictive, people will work around them, negating their benefits, so this is a tricky balance to get right. Decouple the places where people make the most mistakes from the places where they can cause failures. In particular, provide fully featured non-production sand environments where people can explore and experiment safely using real data without affecting real users. Test thoroughly at all levels, from unit tests to whole system integration tests and manual tests. Automated testing is widely used, well understood, and especially valuable for covering corner cases that rarely arise in normal operation. Continuing on the best practices, we should allow quick and easy recovery from human errors to minimize the impact in case of a failure. For example, make it fast to roll back configuration changes. Roll out new code gradually so that any unexpected bugs affect only a subset of users, and provide tools to recompute data in case it turns out that the old computation was incorrect. Set up detailed and clear monitoring such as performance metrics and error rates. In other engineering disciplines, this is referred to as telemetry. Monitoring can show us early warning signals and allow us to check whether any assumptions or constraints are being violated. When a problem occurs, metrics can be invaluable in diagnosing the issue. Implement good management practices and training. Now, let's look at scalability. Scalability is the term we use to describe a system's ability to cope with increased load. Note, however, that it is not a one-dimensional label that we attach to a system. It is meaningless to say X is scalable or Y doesn't scale. Rather, discussing scalability means considering questions like, if the system grows in a particular way, what are our options of coping with the growth? And how can we add computing resources to handle the additional load? Now, let's describe performance in the context of scalability. When you increase a load parameter and keep the system resources like CPU, memory, network bandwidth, etc. unchanged, how is the performance of your system affected? When you increase a load parameter, how much do you need to increase the resources if you want to keep the performance unchanged? Now, let's look at latency and response time, again in the context of scalability. Latency and response times are often used synonymously, but they are not the same. The response time is what the client sees. Besides the actual time to process the request, that is the service time, it includes network delays and queuing delays. Latency is the duration that a request is waiting to be handled, during which it is latent, awaiting service. Now, let's look at the definition of tail latency amplification. Even if only a small percentage of backend calls are slow, the chance of getting a slow call increases if an end user request requires multiple backend calls. So a higher proportion of end user requests end up being slow. Let's discuss maintainability. We can and should design software in such a way that it will hopefully minimize pain during maintenance and thus avoid creating legacy software ourselves. To this end, we'll pay particular attention to 3 design principles for software systems. First, operability, making it easy for operations teams to keep the systems running smoothly. Simplicity, making it easy for new engineers to understand the system by removing as much complexity as possible from the system. Note, this is not the same as simplicity of the user interface. The third one is evolvability, making it easy for engineers to make changes to the systems in the future, adapting it for unanticipated use cases as requirement changes, also known as extensibility, modifiability, or plasticity. Now, let's look at simplicity, that is managing complexity in the context of maintainability. One of the best tools we have for removing accidental complexity is abstraction. A good abstraction can hide a great detail of implementation details behind a clean, simple to understand facade. A good abstraction can also be used for a wide range of different applications. Not only is this reuse more efficient than re-implementing a similar thing multiple times, but it also leads to a higher quality software, as quality improvements in the abstract component benefit all applications that use it. Now let's talk evolvability in the context of maintainability. In terms of organizational processes, agile working patterns provide a framework for adapting to change. The agile community has also developed technical tools and patterns that are helpful when developing software in a frequently changing environment, such as test-driven development or TDD in short, and refactoring. The ease with which you can modify a data system and adapt it to changing requirements is closely linked to its simplicity and its abstractions. Simple and easy to understand systems are usually easier to modify than complex ones. But since this is such an important idea, we will use a different word to refer to agility on data system level. It's called evolvability. This concludes Chapter 1 notes. Hope this was useful. Have a nice time. Like and subscribe for more such content.